Hi everyone, I used some notes I took in class today to determine what I thought people were having trouble with, and I decided to assemble a translation. I hope this video is a little more time. So the first one I want to focus on is they thought that only if is just equivalent to if. So let's call this P and let's call this Q. And if we see a sentence like it means to us if P then Q, or P horseshoe Q. Now let's look at the truth table for P horseshoe Q. See if that really means Q only if P. And immediately we'll see that actually it doesn't, because in this row the horseshoe connective is indeed true. However, the atom Q is true when P is false. So what the horseshoe is actually saying is that in which P and Q have their respective values, the horseshoe is not true in any row where P is true but Q is not. So the premise only if the conclusion. It cannot be the case that the premise is true but the conclusion is false. I hope that makes some amount of sense. So the next one is we can tackle it as a translation problem without any use of truth tables. So let's just give all these atoms their own and we'll always use the positive version of the proposition. So P is Paul sings. And since we have this right here, I won't bother. So let's look at the first sentence. We're talking about two atoms. So we know we're saying Paul doesn't sing and George doesn't sing. So we're saying something about not P and not Q. And what is the connective here? Well, if Paul doesn't sing whenever George doesn't sing, then that means if George doesn't sing, then Paul doesn't sing. Paul doesn't sing whenever George doesn't sing. So we actually have not Q implies P. For the second premise, we have George and Paul both sing only if John doesn't. And we remember from the last example that only if just means the horseshoe. It goes in the same direction. So we have P ampersand Q, and we'll put brackets around those two, implies only if not R. It's very tempting to write not J there, but I won't. So therefore, and here's the rub, either John doesn't sing, or whenever George sings, so does Paul. So we have some nested propositions here. So let's just start this right off the bat with not R. That's easy. John doesn't sing, not R. We know that that's good. It's what we want. And we have an either or here. And we know that that's just a disjunction, so we'll throw in a wedge. R wedge. And then we have another, a sort of nested proposition. There's an if statement within this main one. So we'll have to put brackets around it to show that it's its own little if statement that if these two weren't atoms, earlier in the argument, it could actually be an atom of its own. So, whenever George sings, so does Paul, is Q and P in brackets. And what's the connective here? Whenever George sings, so does Paul. If George sings, then Paul sings. Does that imply that if Paul doesn't sing, then George doesn't sing? I don't think so. So instead of a biconditional, we have a regular conditional, which is a horseshoe. So this, if I have my logic right, is the translation of the whole argument. Then let's tackle this one. It's both the case that Paul doesn't sing and that George sings. John and George both don't sing, or else either John or George sings. Therefore, George sings just in case both Paul and John don't sing. Oh, excuse me. We'll use the same atoms as before, just to save ourselves time and colors. So let's look at this. It's both the case, and we know immediately that we're going to have an ampersand in here somewhere. And we have Paul doesn't sing, and that means not P. Not P. And that George sings, which is Q, and these are connected by the ampersand. This is our whole first proposition. It's both the case that Paul doesn't sing and that George sings. John and George both don't sing, or else either John or George sings. And this is actually a rather silly tautology, if you can recognize it for what it is. But let's write it out. We'll have it is not the case that it is the case that not R and not Q. And you can also write this as not R wedge Q. And I'll show you why this follows in just a few minutes. Or else. So this is another wedge statement around it. Or else either John or George sings. Either John or George sings. I keep calling it V, it's really a wedge. R wedge Q. So we can see here, if you actually think about it hard enough, that's that premise is a tautology. It's trivial. It's the case in every possible world, because all it says is either it's the case that neither sings, or it's the case that one of them sings. So either one of them sings or they don't. It's yeah, that pretty much covers it, doesn't it? So let's go to the final conclusion. Therefore, George sings. George sings, just in case both Paul and John don't sing. And that's the same thing, again, as neither Paul nor John sing, but we'll treat it as not R and not Q, because that's kind of closer to how it's phrased in the question. Now, what's the connective that we're using here? Just in case. What does that mean? Now, I'm going to be honest with you. I don't really see any reason why this connective should not mean the same thing as only if. To me, I cannot see anything that adds any extra meaning to it that it would mean anything other than only if. However, for purposes of logic and for this class, just in case means the try-bar, if and only if. This should be not P, not Q, but for purposes of translating the connectives, it doesn't really matter. We're not evaluating the argument. So anyway, this is the try-bar. Don't ask me why. Ask Jordan to explain it. I don't really know. So here is an example that's from our textbook. It's from one of the early chapters, and it's kind of like a little toy example. But it's kind of good, I think, for getting the really basic stuff down. So Yukiko is a linguist. We'll call that P, of course. Only if both Pavlos is a logician and Christine is not a lawyer. So right away we'll have P and Q and R. And let's just translate this really quick. So we already established that only if means the horseshoe. So Pavlos is a logician, but Christine is not a lawyer. So we'll have a tilde here. And these two are both the case. So they have an ampersand. And I just want to pause here and do a little mini lesson on how to draw the ampersand, because this poor creature is slaughtered so often, including by our prof. And I just want to show everyone how to do it. So you start at the bottom right of where you're going, and go up and to the left, and swoop back down around, but also towards the left. Bring up the curve kind of like a C, and curl around here. Or, if you want to do it the really easy way, do a backwards 3, and put a line through it. This poor little connective does not deserve your abuse. So now that we're done defending the moral integrity of the logical connectives writing, which is very hypocritical of me considering my handwriting, let's tackle this example. If you're going to the party, Max won't come. If Max comes to the party, I'll have a good time if Julie's there too. Therefore, if you're going to the party, but Julie's not, I'll have a good time. So this argument seems a little weird. So how do we translate it? How do we get this on the board? Again, excuse me. Again, remember we always use the positive version of the atoms in our translations. So let me move this back down a little bit. There. So if you're going to the party, will be P. Max comes to the party will be Q. And Julie coming to the, having a good time will be R. And Julie coming to the party will be S. Let's pick a good color for S. We'll make it gray. S. Actually, no, let's make it purple, because I haven't used that yet, I think. So we have P, Q, R, S. So let's get this pretty quick. This first one, I think, should be obvious. It's a simple if-then statement with a negation. So P implies not Q. Then we have another if-then statement, but this one is a little bit more complicated. If Max comes to the party, then I'll have a good time if Julie's there too. So this is nested. We have an implication, a horseshoe, on another implication, horseshoe. So Max comes to the party is Q. having a good time is R, and Julie being there is S. So if Max comes to the party, I'll have a good time if Julie's there too. So yeah, he apparently doesn't like this Max person. So therefore, if you're going to the party, P, but Julie's not, which is ampersand, not S, then that implies R. And I hope we can see why it's important from this argument to use the positive versions of the connective always, because then we would have a lot of weird. If it's negated and not negated in the same thing, then it doesn't matter which one you said first. You'll end up with some weird things where you'll have a positive proposition represent a negative, and you'll probably end up confusing yourself. So now that we've gone through a few different examples, let's actually get the rules for translating the conditionals on the board, and see what English terms usually represent them. So the conditional is the horseshoe, and this has if P, then Q. P only if Q. When P, I should use a different color for that. When P, Q, whenever P, Q. These are all just different ways of saying the same thing, and hopefully from the truth table I did above, that should be clear as to why that's the case, and we won't have to talk about it anymore. If it's still not, feel free to message me or go talk to Jordan or whatever. It's your call. Just moving this up a bit. So a negated conditional. So that is an argument of the form, simply that it is not the case that P implies Q. So any other form that you have here is not a negated conditional. If it's that not P implies Q, or P implies not Q, or not P implies not Q, none of those are negated conditionals. A negated conditional means it is not the case that P implies Q, which, if we look at our truth table here, just means that this is true whenever the whole horseshoe truth table is false, the inverse of the horseshoe truth table, so it is only true in this row, P and not Q. So another way of saying this is P and not Q. So whenever you see either of these, you can know that they're equivalent. And if you see something like not P, therefore Q, you should know that you don't put the negation around the whole thing. You would just put it in front of P, like this. If it said, it is not the case that, it is not the case that P, therefore Q, then the conditional would go around the whole thing, because it is not the case that that is something that applies to a whole sentence in logic. So biconditionals are ones that seem to confuse a lot of people. So let's really go over what a biconditional means, and let's look at the truth for biconditional. Let's set that up in here. So we have these rows, and we'll have P, Q, P, if and only if Q. We fill these in with their values, and we look at the truth table, which looks like this. And we see that it is true only in the rows where P and Q are either both true or both false. So another way of writing this is either P and Q, or not P and not Q. Or it is not the case that P and not Q, or not P and Q. And if you actually write out the truth tables for both of these, you should see why they're equivalent. And for this one, you might be thinking, well, isn't this an inclusive disjunction? But I think you'll find that if P, if it can't be the case that both of these are true in any configuration of the truth values of P and Q, and that's what a biconditional means, so that's good. And a negated biconditional would just be the opposite of this. So you would either stick a not around this thing, or you would erase this not, and it would be true in these two rows. Either only one of them is true, and they aren't both false. So you could also use an exclusive or. You could, I don't remember the symbol for an exclusive or, but let's just say it's this, because I don't remember. And we could say not P or not Q, but not both. So it has to be the case that one of them is false, but it cannot be the case that both of them is false. And I think most people are comfortable with the rules for disjunctions. Either or statements are ones that come fairly quickly to most people. We just have to know that in logic we generally mean an inclusive or. So if your waiter is a logician, and he asks you soup or salad, you can say both, and he won't think that you're a total weirdo. Or if oh gee, I don't know, you're talking to your doctor, and she says, do you? She says, are you male or female? But she's also a logician doctor. Then you can say both. I don't know. I'm just thinking of silly examples. So as long as we know that either it is the case that it can include both, then I don't think we really need to say much more on disjunction. But negated disjunctions often confuse people. So let's actually look at the equivalency that is not the case that P or Q is equivalent to it's equivalent to not P and not Q. Let's actually do a truth table for this, just to make it a little more clear in everyone's mind. So we'll erase this so that we can rewrite it smaller. We'll do a truth tree, which for some reason has a little pink square. I don't know why. MS Paint makes me cry sometimes. So let's look at our truth tree for this. We'll have our top row with our propositions, and then since we have 2 atoms, we need 4 rows. And we have 2 atoms in 1 sentence, so 3 columns will do. And we have P, Q. And it's, if they're equivalent, then we should see that neither P nor Q is true if and only if not P and not Q. They're entirely equivalent. So let's push across these values and see what happens. So then we can evaluate these. So P or Q is not true here, and it is true here, and true here, and true here. Not P and not, so we should evaluate the negations first, I guess. So not P is true here, false here, false here. It's just the inverse of whichever one it actually has. And then we can see not P and not Q is true here, and it is false here. Oh, sorry, I wrote a 0 instead of 1. True here, false here, and false here. Finally, we'll negate this whole thing, and we'll see that it is true here, false here, false here, false here. And finally, we will see that this is true. They're the same in every row, and that's what if and only if means. It means that they always have the same truth value. They are the same in all rows. The proposition that contains blah if and only x bloop is a tautology. So hopefully that should make that a little bit more clear for everyone.